So here we have a new game, and if we think about, so now that we know how to do successive iteration of dominated strategies, we can try this one. So I will pick a row move, and you'll pick a column move, and we'll see. Okay, I selected move A. So if you chose 1, I scored 3 and you scored 2. If you chose move 2, we both scored 0. Um, in terms of dominated strategies, there are none. 3-0 is, 3 is preferable to 0, but 2 is preferable to 0. And same here, 2-0, 3-0. So we can't eliminate any of these strategies based on dominant strategies. And so our solution method does not work for this game. We cannot, based on our previous solution strategy, come up with any sort of conclusion. This is a coordination game. It's called Battle of the Sexes, and it's meant to relate. You've got two people that want to. They're interested in spending time together, but row player has a preference for activity A, and column player has a preference for activity B, whatever that is. So imagine a couple going out on a date, and we have what he wants to do and what she wants to do, and obviously they want to show up at the same place, and they're much happier than being apart, but they want, he wants to show up here, and she wants to show up over here in location B. This is not a zero-sum game, since everybody can win. It's just sometimes there's a better winner than others. And so this type of game is often used to model coordination problems. So if we're all trying to accomplish something, but we also have our separate conflicting interests, we want to be able to organize our life so that we can coordinate around some beneficial activity so that everyone can win in a good way. Another example where we have no strictly dominated strategies is in this game. So we want to come up with a method for being able to handle games when we don't have a strictly dominant strategy. And for that we need the concept of Nash equilibrium. So John Nash is the mathematician in A Beautiful Mind. They sort of talked about the Nash equilibrium in the bar scene in that movie, although it don't use it as a reference because they kind of messed it up. And in any case, the Nash equilibrium is a specific kind of equilibrium of a game that depends on keeping track of the strategies of the other players. So suppose instead of knowing the move my opponent would pick, I knew their strategy plan. So if I play move 1, they'll play move A. If I play move 2, they'll play move B. If I play move C, they'll play move 3. They don't actually have to know my move. The strategy sets can be dependent, and the key is to find a situation where, based on what they're going to do, my best interest is to have a particular strategy set, and their best interest is to have this, their own strategy set, and you don't benefit from deviating. So that's the key, is that you can't do better by doing something else because of what the other player is doing. So we can think, just to do an example of this, so we've got our game here with 9 different things we could do. If I suppose that I, as the role player, always play role B. Well, if the column player knows they're going to get 2 points no matter what, and let's say their strategy is to play column 1 no matter what. Well, that's not going to be an equilibrium, because if I know they're playing column 1, I'm going to play move A. So I have a preference for A over B given what they're doing. I mean, obviously A isn't better than B all the time. If they play 3, it's not. But I don't have to worry about 3 because they've decided to play 1 all the time. So that result is not an equilibrium. To be an equilibrium, you have to get back to where you started. So if I play B, and their best response is to play something, and then my response to that is to still play B, that would be an equilibrium. And we can accomplish that by selecting B, and then having the column player select move 2 instead of move 1. That's just move 2 is just as good for them as move 1, so there's no reason why they couldn't play that all the time instead of move 1. And if that's the case, then the row player, given column 2, A, B, and C are all just as good. So in response to move 2, I could play A, I could play C, I could play B. Since B is one of the things I could pick, I actually achieve an equilibrium. So I started with B, they responded with 2, I respond with B, they respond with 2, and so on. I mean, we're only playing this game once, but my best response to their strategy and their best response to my strategy is to do the same thing. So everything matches up, and B2 is a solution to this game. But in general, a Nash equilibrium is it's actually a set of the strategies of both players. So you can't just describe a move, you have to describe a strategy. So in my case, my strategy was play B all the time, and their strategy was play 2 all the time. But we could specify a different strategy. So suppose my strategy was to play A 1/3 of the time, B 1/3 of the time, and C 1/3 of the time. Well, the best response of the column player to that might be to play 1 1/3 of the time, 2 1/3 of the time, and 3 1/3 of the time. And given that that's what they're doing, if I go back and look at my strategy, that's actually a good thing to do, right? If they're here sometimes, I want to be here sometimes. If they're here sometimes, I want to be here sometimes. And everything's symmetric, and so we're going to get this this equal sharing. The course software that comes with our book can solve zero-sum games. In the game theory quiz, you could be asked, what is the solution to a game given a particular solution strategy, or to check if a given equilibrium is a Nash equilibrium, or given a set of 4 different strategy sets, which is a Nash equilibrium for a particular game presented. So all the games are, none are of this size, it's all 2 moves and 2 players. But both the notions of successively dominated strategies and Nash equilibrium come up in the quiz questions.